So chapter 8 is all about types of chemical reactions. And in this chapter, there's several things we got to do. Sam, thank you. One of the things that you have already done with this chapter is balancing equations. And some of you kind of looked at me yesterday and were like, I forgot how to do that. And every year I hear the exact same thing. But I can assure you by the time that we're finished with this, you'll be able to balance any chemical reaction. Because, one, your brain is a little smarter now than it was in 8th grade. And number two, there's a potential that I'm going to teach it a little bit differently, and it's a little bit more efficient of how I'm going to teach you how to do it, instead of just saying, here, figure out these magical numbers to make it work. But the thing that we have to go through and figure out in this part is the types of reactions, and those are things that you've probably never heard of, and so we're going to get into some of those today. Now, some of you did not do really well on this. You just read stuff versus actually looked at it. But we'll go through and we'll talk about it. So, do atoms rearrange in predictable patterns during chemical reactions? That is a question, and what is the answer to that question? It is a resounding yes. Okay. So we can predict what the outcome of chemical reactions will be based on certain patterns. And that's what we're trying to get you to see in this particular POGL. Recognizing patterns allow us to predict future behavior. Weather experts use patterns to predict dangerous storms so people can get their families to safety. Political analysts use patterns to predict election outcomes. Similarly, chemists classify chemical equations according to their patterns to help predict products of unknown but similar chemical reactions. And so then they give you this big old list of crazy, convoluted chaos. That there's specific reactions going on in this in each set. So let's look at each set individually and let's kind of see what's going on. My first thing that I need you to all understand is what a chemical reaction is composed of. And if you want to write this at the top, this may be a good idea. So chemical reactions. First of all, you do know that RxN is reactions, right? Okay. What do reactions start with? Reactants. And this is my shorthand. Reactants. And then what goes in the middle of this thing? An arrow. Now, what is the chemical name for that arrow? Yields. Thank you. So, what is another way to say yield? No. Make, create, anything else? Produce. Anybody? So reactants, yield, make, create, produce what things? Products. Or prods. Okay. So we've got to find what's happening on one side, and then when those things react, what happens on the other side. So what is essentially the outcome of the chemical reaction? So let's go in and let's look at part A. Your first focus needs to be, where is the arrow? There, 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 and there. Now, so tell me some of the similarities that every single one of these reactions have in common. The what? The what's on the left? What do you mean by the addition? Be a little bit more specific. Okay. That's what I wanted to hear. You're adding what? Two things together. So do you agree that there are two reactants in all of those particular reactions? Okay. And then what are all of those two reactants doing? Making one product. Would you agree that those are all similar things? Okay. Now, are there any dissimilar things up there? What are all of those little letters inside parentheses stand for? State of matter. So this may be another little note that you want to write down. Okay. States of, and again, this is not something that I'm just doing at random. These are all things you're going to have to know. So I'm not wasting time. I'm actually teaching you as we're going through this. So if you see a parenthesis with an S inside of it, what does that stand for? Solid. Okay. If you see a parenthesis with, now I just draw my lowercase l's like that just for effect. But what is a lowercase l? A liquid. Okay? And then what happens if you see a little g? It's a gas. Now, more than likely, you knew all of those three before you ever walked into this door. But there's a fourth one that we need to talk about. What is the other thing that showed up in parentheses that you'd probably never seen? AQ. And I want you to kind of put it right here. AQ. What does AQ stand for? Aqueous. Aqueous. So here's the deal. Students always get these two things confused. Because if I asked you to get me an aqueous, matter of fact, let's do this as well. Out here, you may want to put in parentheses or brackets the word solution. Because sometimes those two words go together, sometimes they're apart, but they mean the same thing. So if I said, get me an aqueous solution, what would it look like physically? Don't say water. It would look like a liquid. Okay, water is not the answer to every question in chemistry. It would look like a liquid. But here's the deal. It looks the same, but is it chemically the same? And here's the major thing that I need you to know about liquid. That it is pure. It is pure. And what does pure mean? Try. Sir, go ahead.
100%. It's composed entirely of the same thing.
Perfect. That's exactly the right answer. It's 100% of exactly whatever you're talking about. So Dalton, you're drinking a bottle of water. That water that you're drinking, is that pure 100% H2O?
It's spring water.
Is it? You just told me it's got minerals in it. So is that 100% H2O in that bottle?
It says pure quality.
They're lying. They're lying to you. Funny story is, you know that bottle pure water that says it has electrolytes in it? It's a lie. It doesn't have any. Yeah. So here's the deal. So if I say I need some mercury, when I say mercury, you know that means what letters, first of all? Hg. So what color is it up there? It's probably easier to see it on that one. It's a blue color, which means it's in what state of matter at room temperature? Liquid. So when I say that is mercury or pure mercury or elemental mercury, is there anything else in that bottle other than the element Hg? No, that bottle that he's drinking of water. So technically it's not pure water. It's technically a what? A solution. Because here's the difference. Aqueous things are mixtures. Sir? No, that's the ion form. We're talking about pure elemental. Yes, and we'll talk about that. I promise I'll get to it. Now, how many of you have contacts? How many of you take them out at night? You put them in the little dishes, right? If you don't take them out at night, probably a good idea to do that. So what is that stuff you pour on top of them? Contact solution, right? So what's in that bottle that you're pouring on it? It looks like water, right? It's a saline solution. So there's all kind of stuff in there to freshen up those things. You're not pouring a liquid on it. So this is a difficult thing for students to compartmentalize because visually, does it look like it's a bottle of water? But you know that it's a solution because there's other stuff mixed in with it. So when you see the letter AQ, that means it is a solid dissolved in what? Water. Now, this is kind of, let me actually do this. I'm going to put quotation marks around the word water. Now, I'm reaching way back here to ask you this question. Way back. What is it? What is that thing called that does the dissolving? Someone other than Dustin? The solvent. Someone other than Dustin. What is the thing that gets... Someone other than Dalton. Solute. Okay. Water is known as the universal solvent, but is it the only solvent that you have? No, there are many, many, many solvents. Alcohol is also a useful solvent. Okay, ladies, whenever you paint your fingernails, what do you get it off with? Did you say acid? Acetone. Okay, acetone is an alcohol-based product. Okay, that's why it smells so bad. But it's a alcohol-based substance. It's also got a little bit of water, but it's mainly alcohol. So a solid dissolved in, again, quotation marks, water. But here's the deal. When we talk about mixtures and we talk about solutions, here's the other difficult part about this is that solutions don't technically have to be in a liquidy form. How many of you play a brass instrument? Okay, what is a brass instrument? It's made up of copper and zinc mixed together. Now, when it's a solid metal mixture, it has another special name. It starts with an A. Okay, it is an alloy. But here's the whole thing that I'm trying to get you guys to understand. And I'm going to come back over here and let's look at this. So right here, it has water as an L, but it has MgOH as AQ. So what does this mean when it says H2OL? That means that if in that thing, whatever you're containing that H2O in, what is the only thing in that container? Pure H2O. 2 hydrogens and 1 oxygen chemically bonded together. Now, we have a special name for those types of water. What is that special type? Distilled, deionized, anything like that. So distilled, and then you can actually go buy distilled water. Don't drink it. It's not good for you. Yeah, it'll actually dehydrate you. Is that what your question is? Can I drink it? Okay, yeah. You can. It's tasteless. It's kind of bitter, and it's actually not good for you. You actually need the fluoride and the ions that are in tap water. Yes, ma'am. It's kind of one of those things you're like, that did not taste good, but it didn't have a taste. It's one of those things that's hard to explain without doing it.
Water itself, I'm not able to explain it. It's supposedly very healthy for you, but it has no nutritional value whatsoever.
That's not true because you can't live without it.
Exactly, but if you look at the nutrition facts, it's 0% everything.
Because we're 95% water. We have to replace that.
We're 67% water.
Are we 60?
Jellyfish are 95% water.
Yo, I wish I was a jellyfish.
Okay. Now, let me ask you something here. So watch what happens. So if I take iron, stay with me, guys. Stay with me. If I take iron, which is a solid, and I react it with oxygen molecules, I get this thing called iron oxide. Now, this particular reaction right here, what is this right here? That is technically rust. Okay, so that top reaction is rust. Now, this next one, we have nitrogen gas plus 3 hydrogen gas molecules react to form what? What is NH3? Come on, what is NH3? Ammonia. Ammonia. Now, do me a favor, write this out beside this, please. This is known as the Haber-Bosch process. B-O-S-C-H. Haber-Bosch process. Now, why in the world would we need a process to produce ammonia? What is ammonia used for? Fertilizer. Okay, so what happens is they take, how much of the atmosphere is composed of nitrogen? About 70-ish%. Is hydrogen also floating around? So they can literally take the atmospheric air, pull it in, purify it, react it, and produce a whole ton of ammonium. And so then what they do is they take that ammonia, and do a few other chemical reactions with it and create ammonium nitrate, which is then put into fertilizers. Now, if we have some time at the end of class, I will show you this. There was a fertilizer plant out in Texas a few years back that was producing this stuff, and something happened and it ignited. If you haven't seen it, it's an amazing sight to see. I'll try to find it for you at the very end. Now, the other thing that I wanted to show you guys was this. It's a gas plus a liquid and it turns into aqueous. So again, here's the deal. What is, and this is a super silly simple question, what is a gas inside of a liquid called? A bubble. A gas inside of a liquid is called a bubble. How many of you drink bubbles in liquid every day? You should all raise your hand if you have carbonated beverages. Okay? Because here's what happens. The carbon dioxide is dissolved into the liquid. So anytime you have something dissolved in water, what state of matter is it in? Aqueous. So look at the product right here. So we have this stuff, which is aqueous, and that actually is sulfuric acid. Okay, this is actually sulfuric acid, and the way you get it is by bubbling sulfur. What is that reactant? Sulfur something oxide? Trioxide, bubbling it in the water, and it creates sulfuric acid. Okay, so that's set A. Now let's move over to set B. I'm not going to spend near as much time on this one. So what is common about all the ones in set B? Okay, the first thing you need to do is find all your arrows. So there's an arrow, there's an arrow, there's an arrow, there's one, and there's one. So what do you notice about all of those? You've got one reactant, and what are they doing on the other side? They're breaking down into two or more things. Okay, so notice again, you've got several solids, even liquid, decomposing into it. Look at the third one down. What's happening physically? Okay, no, what's physically happening? You're literally ripping a water molecule in half. Okay, do me a favor out beside this. Please write the word hydrolysis. Yes. You can take a 9-volt battery. Does everybody know what a 9-volt battery is? You can take alligator clips. It's like mini jumper cables. You know what I'm talking about? Okay. You can put it on 2 pieces of graphite pencil lead, stick it in the water, and make it bubble. Okay. So what's happening is the electrical energy is running through the battery, from the battery through the wires and into the water, and it's actually doing a hydrolysis. Okay. And so you're actually split. You know what? I'm so dumb. Yes. Wait a second. Hold on. Please erase that and write electrolysis. Well, that's your fault. What happened to that pencil you were working with earlier? Exactly. Now, so the one last thing that I want to show you is, can one reactant decompose into more than 2 things? Look at the very last reaction. Now, hopefully you know this. What is the name of that thing? Ammonium carbonate. Ammonium carbonate will produce ammonia, hydrogen, and carbon dioxide. Now, there is one thing that we will get to learn, that carbonates. Every single time you have a carbonate, you're always it will decompose into those 2 things. Always, 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 always. Yes, sir. What? Did I say water? Oh, okay. Ammonia, water, and carbon dioxide. We really out of time? 38. What time is it? I got 4 minutes left. Hold on. No. I got 4 minutes left. No, stop. Now, I'm going until everyone else leaves, so y'all stay with me. Now, set C. What's happening in set C? Okay. So if you look at this, you've got a compound plus one thing produces one thing plus a dissimilar compound. And so hopefully you guys kind of saw how this all worked out. Because if you notice, one of the thing in front sometimes swap with the thing that was by itself. And we'll kind of get to what's happening over there. And then over here in the set D, what's happening to those 2? Everything is swapping place, right? There's nothing that does not swap places. Do me a favor. Besides set C, please write this down. And I promise you we will get to this. But please write by set C, need activity series. And I know what you're saying. What is the activity series? Again, we will get to the activity series. You just got to be patient with me. All right, so let's just go let's try to answer these first three questions. The chemical equation in Model 1 contains the phase notations S, L, G, and AQ. Match each symbol with its meaning. Dissolved in water. So what should you have under that? AQ, liquid is L, solid is S, and gas is G. Number 2, based on the examples provided, which set of reactions in Model 1 typically involve ions in solution? And that was the part that you had to kind of look at all the set of reactions. And I think I told you that ions in solution stand for AQ. And which one of them are mostly AQ? C and D. Okay, because like I said, a lot of these are going to end up being C's and D's. And whenever we get to electrochem reactions, we'll talk about those. And number 3, based on examples provided, which set of reactions in Model 1 typically involve gas or solids? A and B, very good. Okay. Number 4, match each description below to one of the reaction sets. Ionic compounds dissolved in water switch partners. Okay. One compound breaks into elements or smaller compounds. That should be easy. That's B. 2 or more elements in a compound combine to form one product. That was A. And then part of an ionic compound is removed and replaced by a new element. That was C. All right, so it should be D, B, A, C. All right, we'll start with 5 tomorrow.